All right, happy day, friends. We're going to get started this morning with a little bit of relativity. We're going to do relativity for the first couple of days here. This is Wednesday, so we'll do Wednesday, Thursday, and probably next Tuesday, maybe a little bit more on relativity, and then we'll switch into quantum mechanics. So, want to just remind you of a couple of things. PLC 11 is a traffic light, so please make sure that you get that turned in. This is an easy one to let go of, seeing as how it's post-celebration, but nonetheless, please make sure you look through them, self-assess. Hopefully you had a little bit of time to do that beforehand, but if not, still go ahead and fix that up. That's Friday as usual. And homework set 7 I will post soon, and that's going to be on special relativity, and we'll see how far else we go. I haven't quite figured out whether or not to include some of the other stuff, so we have either a shorter or a longer homework set. So we'll figure that one out. Hopefully Celebration 2 went reasonably well for you. And we are ready to roll into the new topic, which is going to be modern physics. And so that's going to be, like I said, special relativity, which will comprise for about a week, maybe a week and a half, and then we'll roll into quantum mechanics and the foundations of, or at least the introductory foundations for quantum mechanics. All right, so let's go ahead and get started with some relativity. So when people say relativity, immediately Einstein comes to mind. But in fact, the question of relativity has been around in mechanics for much longer of a period of time. Certainly since before Galileo, because Galileo was the first one who tried to answer this question. So we're going to talk about what relativity means in this context, and what we have in terms of kind of already things that are set in place for us to know about, like in the sense of Galileo's answer. And then we'll turn to the Einstein viewpoint and see what happens when we go there. So relativity is essentially the question of, look, something happens over here. There's an event. Typically the word for this is event. There's a thing that happens. There's a firecracker exploding. There's a lightning strike going on. These are examples that I'll be using. Something's happening, okay? Something's happening. The question is, where and when is that happening? So maybe you can see kind of right away that it needs a coordinate system. And depending on your coordinate system, the answers will be different. So if I'm a person standing over here and I say, well, my coordinate system is origin is over here, and I'm doing this, that, and the other. Okay, fine. The answer that they give is going to be different from an answer if you have your origin. The person has an origin over here, and they're looking backwards this way at it. They're going to give different numbers. Okay, but ultimately, that's not the problem. Okay. The problem is not in the stationary observation of an event. It's in the perspective of what happens when you observe the event and its consequences from a stationary frame, and then you want to know what it looks like from a different frame. That's what relativity basically is trying to get at. So the idea of, suppose I have a stationary Earth frame here. It's attached to Earth. And I'll call this the S frame, because that's the usual notation. But the S frame is a frame of reference in which, let's say it's attached to Earth. So we'd say it's an Earth observer perspective. All right. Now, the question of relativity comes into play when there's a frame moving with respect to this. So someone's on a bicycle or a skateboard or car, airplane, train, whatever it is. We will end up using trains extensively. It's moving with respect to the ground frame, and therefore we want to know what would it look like, what would this event, look like if we had jumped onto the frame of the train. So that frame, I'll draw in blue here, it's known as the S prime frame, and it is typically moving with some speed v relative to the Earth frame. Okay, the S prime frame is moving with respect to the S frame at some constant speed, which we'll call v, and that's a constant velocity, straight line, direction, no change in speed. So we say it's moving with respect to the S frame. So from the S frame observer, we would say, all right, I'm going to go ahead and take my measurements, and I'm going to say I have a set of coordinates for this thing, and I have a time for which it happens. So let's just say we have a set of coordinates. Now these coordinates could be the usual 3-space coordinates. We're going to say that we're only going to deal with one dimension because we need to start off a little bit more easy. But nonetheless, in principle, the S frame observer measures a set of coordinates, which is an X, Y, and a Z for this event, as well as a T for when the event happens. Okay, so this person says, okay, I've got a set of coordinates, which is these 4 things, and I need to catalog what those are. Okay. All right, so we've got a set of coordinates from the S perspective here. They say I have, so and so many meters in which this event happened from my origin, and it happened at some time. Okay. The question of relativity then comes in and says, well, if I was on the moving frame here, what would that set of coordinates look like? In other words, since I call this the prime frame, I'll just call these the prime coordinates. In other words, what are X prime, Y prime, Z prime, and T prime if we know what X, Y, Z, and T are? That's basically the question of relativity. All right, so how do we get the prime numbers from the regular ones? And presumably the speed, the relative motion between the 2 frames. So that's the basic question of relativity. So like I pointed out in the beginning, this question has been around since before Galileo. Galileo was kind of the first one to give an answer to it, but nonetheless, it's a fair question. People have been moving around on ships and walking and all these types of things for a long time. So the question of how does physics change when you put yourself onto a moving platform, or a moving frame of reference? How does it change? What looks different from this perspective relative to the one where we were at rest on Earth? Okay. For a long time, people thought there was a big difference. And it turned to Galileo eventually to say, actually, there's not really that big of a difference. So Galileo was the first one to come up with the idea of the law of inertia. The idea that if you drop something, then it should go straight down. Now, if I'm on a boat moving on a constant velocity across a lake or something like that, and I do the same thing, then there will be no difference. And then you come to the idea of, okay, what happens if you're in a dark room and you can't tell if you are in a room that's stationary on Earth or if it's a room that's stationary on a train, which is moving with respect to Earth, and I do the same experiment, if I get the same result, in principle, I can't tell the difference whether I'm stationary on Earth versus moving with respect to Earth's surface at a constant velocity. There's no experiment that can be done such that you could tell the difference. And Galileo was one of the first people to come up with this idea. Ultimately, it was adopted by, well, Newton used it as well, but ultimately it was adopted by Einstein when he started to answer this question about relativity. Okay, so let's just take a quick look at what Galileo's answer to the relativity question is. The relativity question is, I have a distance here, which I'm going to call x, like that. There's a distance, and there's a time that the Earth frame would measure on their clock for this event happening. Okay, and oh, by the way, like I said, we're just going to stick with x and t, and we're not going to delve into y and z for this. It'll just be essentially one-dimensional kinematics for this introduction. All right, so the S frame has a distance x. The S prime frame has a distance, say, x prime to this event. And we're going to make the assumption, which we will, by the way, constantly make this assumption, that when these two origins moved past one another, the clocks both got set to 0 or noon or something. They both agree that when our two origins coincide, we're gonna push go, or we're gonna push reset on our stopwatches, however you like to do it. Okay, so here we're gonna say that t and t prime are 0 when the two origins coincide. Okay. So that essentially, if we look at the time, then the distance that this prime frame has moved will be knowable, right? That would be, in other words, this distance here should be v times t. So Galileo provided the first answer to the question of, well, where and when is this event occurring from the motion in motion frame, the prime frame. Over here. Okay, so Galileo's answer was that the time that t prime is equal to t. Right? We measure the same number of seconds. If you're on a train, your clock is ticking exactly at the same rate. Nothing is out of the order there. And therefore, x prime, right? If you just look at the addition going on here, it's just x minus vt. This is the succinct answer. Galileo gave a better answer than what I'm giving right now, but I'm trying to simplify. Nah, I'm just cutting straight to the chase of this one. Okay. So essentially, this is what Galileo said is the answer to the relativity question, and that's it. And we're done. And there would have been no problem with this whatsoever. And in fact, we still use this, just like we still use Newtonian mechanics. Just like we still use Newtonian gravity. NASA uses Newtonian gravity to calculate orbits of satellites. Where do they need to go in order to land on this asteroid? They use regular Newtonian gravity. Okay. So why do we need all this extra stuff? Why is Einstein even a part of the picture? Well, something happened. So what happened was, oh, let's see if this thing works. Oh, this works pretty well. Now it doesn't work very well. As soon as it gets a little bit of ink in it, now it doesn't work very well. All right. So what happened was, people were doing experiments with electric charges. All right. And so what happens is you can use a voltage to accelerate an electric charge. And electrons were discovered by Thomson in the late 1890s. And so when they said, oh, well, let's start thinking about shooting these things places, right? I can accelerate an electron with a voltage. All I got to do is hook up my battery to these two plates and repel the electron with this plate and attract it with this plate, then cut a little hole in it so it misses and off it goes. Great. Okay. So suppose that you put a particular voltage through here. And eventually, people were able to come up with fairly large voltages. Okay? So it wasn't too far along before people started realizing, yeah, we can make really big batteries. Okay? So let's suppose that they accelerate it with a 1 million volt potential difference. The electron reaches a particular speed. Okay? And then they doubled that voltage, but the electron did not double its speed. So they provided the same amount of, they provided a particular energy, and then they provided twice that energy. But then all of a sudden, the electron's not attaining twice its velocity. It's not going twice as fast. So why is that? If I'm pushing on it with twice the force, and I'm doing it for the same amount of time, why isn't the electron coming away with twice the speed, right? So this is a typical mechanics, like conservation of momentum, or a momentum impulse question, okay? Or you might like to think of it also as a energy conservation question. Either way, right? If you think about it as momentum impulse, then what you find is that you pushed on the electron for a certain amount of time, and then you doubled that force and pushed on it for the same amount of time. Okay? But the result of this was a mass of the electron times delta V, which is the change in the speed of the electron. Okay? But this does not equal m times 2 delta V. They found out that this is not the case. And so this is somewhat problematic. Why shouldn't double the voltage give you double the speed, right? Starting from rest. All right, so this was found. In other words, the increase in speed is not linear. It's not a simple function. Man, what's going on with this board today? Okay. It's not a simple, straightforward linear function. Also, what happened? So this delta V here would be change in momentum. Okay. And classical mechanics tells us that the impulse equals the change in momentum, which it does in this case, but it doesn't, well, it does in this case, but it doesn't give us twice the delta V. All right. And then Einstein found something interesting in some of the ideas of electricity and magnetism. And he found that the magnetic fields are essentially velocity dependent. They exert velocity dependent forces. So he said, well, okay, what would it look like if the velocities were zero? Because the same essential physical behavior has to happen, but what if, instead of standing here on a Earth frame, or an Earth reference frame, and doing an experiment in which a magnetic field affects the motion of an electric charge, right? The electric charge comes shooting in, there's a magnetic field, and it turns the electric charge. He goes, well, okay, what happens if I am on the electric charge? Therefore, I'm not moving, and the electric charge is not moving. So now what happens? Right? So the idea of how do magnetic fields work? How do they come about if you look at it from the perspective of the moving charge? Okay? So the idea that moving charges produce magnetic fields the magnetic field happens to be the B field. So essentially, we're doing an S to S prime jump here, right? I'm looking at the experiment from the Earth frame and the S frame, but the electron or the proton, whatever it is, the electric charge is moving. So from the Earth frame, we would call that the S prime frame, okay? But note, if you're the charge, then you are in the S frame because you don't know that you're moving. Remember, there's no experiment you can do to convince yourself that you're moving at constant velocity. Therefore, if you're the moving charge, then you're not moving. And you are in the S frame, which means that Earth is going that way, past you, and that must be the prime frame moving this way. Okay? So the perspective shift from the drawing that I drew the first time would then become the S frame looking like this, okay? And the S prime frame is now the Earth frame moving backwards at some speed v, okay? So the idea is you are never in a prime frame. The prime frame is always the one that's moving with respect to you, because your origin is always at your feet. If you ever look down and you see your feet, then you're in the prime frame. I'm sorry, you're in the unprime frame. Right? And everything else is in the prime frame because your origin is your feet. So if I look down and I see my origin, well, I must not be moving because I'm always at the origin. So if I move over here and I look down, well, my origin is still here, which means you all just moved that way from my perspective. So this is the beginnings of how you mentally start understanding what is relativity trying to get at. It's trying to get at what does it look like from the, and it's not an easy answer. What does it look like from their perspective? That's not an easy answer. Okay. Okay, so there are some problems with the answer. There are some problems with these answers because ultimately, what is this getting at? If moving charges produce magnetic fields, and I jump onto the moving charges reference frame, then I'm not moving. Everything else is moving past me, and therefore I don't produce a magnetic field. But physically, there has to be the same thing. So if I interact with something in a magnetic way, and there's a magnetic force, I produce a magnetic force on something and it produces one on me, that force has to be there because everybody has to agree that there was a force exerted. That will change the trajectories of things and it will make things different. So everybody has to agree that a force happened. The question is, since forces arise from the fields, what do we say causes the field? All right, so physics is not changing because the force has to be actually exerted. Everybody has to agree on this. That's like an event. So part of getting into the terminology and the understanding of special relativity is understanding what is an event. as well as how do people measure things about that event. And this is just the basics of where and when did that event occur. So an event is a force gets exerted. Everybody agrees on this, okay? And if there's no field to exert the force, then physics is asking the question, how is that force getting exerted? Because ultimately, from the perspective of a physicist, forces get exerted because of fields and their interactions. If we don't have fields, then we don't have forces. So if I jump on an electric charge and I say there's no magnetic field due to this charge, then how is it going to experience a force? And that was what Einstein's question was. Well, that was part of Einstein's question, okay? So there must be something else going on. In addition to these two things of the change in momentum, excuse me, the change in momentum and the electrical and magnetic effects, there were other things kind of going on, but I'll highlight those two as things that give a little motivation as to we got to look a little deeper into what's going on here. Okay, so let's take a look here. So the Einstein answer, the Galileo answer is that we have it all figured out. Okay, but the Einstein answer is that things are not quite that simple, because if I go in and do if I do what's called the Galilean approach to solving this problem, it doesn't work. Okay, and same with this. Why is this not working? The Galileo approach tells us that this should work, but it's not. So what's going on? Well, one of the things that's going on is, let me just share my screen here and see if I can show you some pictures of things. All right. Oops. Okay, let me see if I can share my screen here. So, all right, so I'm doing a share here with let's see, motion of a car and a ball as observed by a frame of reference in which a tree is stationary. Okay, so hopefully you can see this. First question, how do we know this is the tree frame of reference? Well, look where the tree is. If the tree looks down, it sees a zero, so it knows it's not moving. Therefore, whatever frame of reference this is essentially attached to the tree. Okay? And if we jump to different frames, then maybe the tree would move, but right now this is the frame of reference of and the events as seen from the tree frame. And so you'd say, all right, well, at time 0, the tree and the car are lined up and the baseball is at about 2.5 meters away. By time 2, you can see the car has moved 2 meters, and by time 4, the car has moved 4 meters, so the car must be moving 1 meter per second, and the baseball is moving 0.5 meter per second, and so the car eventually catches up to the baseball. Okay? So the question of, for example, what's an event here? Okay? An event would be the car catching up to the baseball. That's going to be something that everyone's going to agree on because a force might be exerted by the baseball and the car on each other. Okay? So if that happens, then it leaves a dent, say, in the car. And the ball goes off in some weird way. And that means that everybody has to agree that the car got dented. Okay? So this is what I mean when I say you think about a force being exerted, it's an event that everyone agrees on because it leaves physical consequences. It leaves evidence behind that there was a force exerted. Something is different now. Right? The car has a dent in the hood. It didn't before. Everybody has to agree there's a dent in the hood. Okay? So if I go from here to, let's see. Can I just move this? If I go from here to here, we still good in the share? Hopefully. If I go here, I'll move this down. If I go here, now look what's happening. This is the frame of reference of the car. So notice that all of the motions are different. Okay? The tree's moving. Tree's moving and it's going towards the left. The baseball is moving. It's going towards the left. It was going towards the right before. It's moving at basically the same speed but the other way, right? The tree is moving a certain speed, which is what the car used to be doing, but it's going the other way. The car is at 0, so it's the car frame of reference. And we're looking at the we're looking at the motions of everything relative to the car now. Okay? Notice, by time step number 4, the ball is hitting the car. It has to, right? We all have to agree that the ball and the car hit each other, all right? Certainly you could go through and do a frame of reference of the ball and see what that looks like. Again, by the time you get to the end step, they're going to be hitting each other. All right, so if we take and look at these from a perspective standpoint, I'm going to zoom in again on this and go down a bit. If we zoom in on this thing. All right, now back to the tree frame. This is going to be, not the tree frame, but this type of diagram is going to be super helpful in interpreting what is going on in a relativistic sense. So, here's the perspective issue of the drawings I just showed you. This is the tree frame. Okay, notice the tree frame axes. The tree frame axes labeled tree up here, and there's a T and an X. I will stop for a minute and say, yes, these are reversed from what you perhaps learned in a 4A class. Actually, if you want the real truth, the 4A class has the axes reversed. They were always this way, and we did it the other way for 4A. Nonetheless, please be aware that the time axis is now the vertical and the space axis is now the horizontal instead of the other way around. That means that the slope of this line is now not simply the velocity, it's 1 over the velocity. Okay, that being said, the tree stays stationary. Okay. You'll notice that the tree stays at x equals 0 the entire way up, the t-axis here, and therefore it does not change its position as time goes on. However, the car goes from 0, which is where it started, out to 1, to 2, to 3, to 4, and you'll see that we've got a line drawing the car positions as time goes on. Okay? Here's a line with the ball positions. As time goes on, lo and behold, they cross, and everybody agrees that they cross. The question is, where does that event happen, right? That's kind of the question of relativity trying to get across. Okay? I want to do this, which is to look at the same perspective as seen from the car frame here. Now the car, notice, is at 0, 0, 0, 0, 0. Here's the car frame. Now this is labeled the T prime frame because we know that the car was moving. Yeah, not necessarily. I would call this the T frame. Anyways, the car is at the 0 point, x equals 0, all along the time. Okay, so its position does not change according to it. The tree moves backwards, right? So that would be towards the left, and that's the tree going that way. And here's the ball approaching at a slightly different speed and eventually hitting the car. All right, now, here is the great news. We can look, and this is why these diagrams are so useful. We can look at both perspectives. I can look at the tree frame and I can look at the car frame on one set of axes. Okay, and so I'll go back to this one to show you how I think of this. So here's the tree frame, it's the earth frame. Okay, now if I scroll down, this is what this looks like if I were looking at the bird's eye view of it. Okay, so there's the tree as it goes up the left side, there's the t-axis going up the left side. The tree's position is x equals 0 the entire time, t equals 1, 2, 3, 4, 5. It doesn't change, it's x position. However, the car's position does move, and the ball's position does move. Okay. What I'm going to say is that we can look at the car frame and the tree frame both simultaneously on this diagram because we can plot the car's axis. So this is the car's motion with respect to the tree, as well as the tree's motion with respect to the car. It's on the same set of axes. It gives us then the ability to be able to see things from two perspectives at once on one set of axes. These are very powerful diagrams. However, don't expect to be able to look at these and go, oh yeah, I got it, no problem, right away, okay? We're going to spend some time trying to tune in what these things mean, what information can you get off them, and how to interpret them. We're going to spend some time doing that because, honestly, that time needs to be spent. So, for example, if we look at the ball from the tree frame, we can see that the ball's position starts at 2.5 meters away and ultimately ends at 5 meters away from the tree's perspective. However, from the car perspective, what happens? The ball starts 2.5 meters away and eventually ends up at 0 meters away, right? Because for the car, its origin is that red line that goes like this, okay? That's what the car's reference frame origin is. Therefore, the ball hits it, which means at some point the ball's position was x equals 0, according to the car, right? So the coordinates of that point will be different, okay, depending on what perspective you choose to look at. All right. So this is step number one. This is step number one. It is to look at two perspectives on a single diagram. I'm going to stop this for a minute. We're going to get back to drawing a little bit here, okay? What this means is, if I draw my X and my T, all right, suppose this is my tree frame, and this is my tree time axis and my tree space axis, okay? And I put the car on here. Did that in blue, so the car I'll put in black. Okay. Now, according to the tree, the car is in motion with respect to the tree. So if I'm in the tree frame and these are my normal axes, this is essentially an Earth perspective. And therefore, the car is moving, so I'm going to call that the T prime axis. Prime is a little big. There we go. That's the T prime axis. Okay. So now, if I want to think about the coordinates of an event happening, well, all I need to do is find out, okay, where is this event? Maybe it's, say, here, right? And I would say, okay, from the from the tree perspective, I'm going to say it happened here, and at that place in space, and it happened at that time. I'm just going to take my usual coordinate axes, right? So this is a coordinate point. Now, from the car perspective, I'm going to say, well, okay, where did it happen? Okay, notice, however, that if I'm going to use the same type of thinking as I did just now to find the coordinates in the TX frame, I'm going to have to do something slightly different to find the coordinates in the T prime frame. Okay, the T prime frame would say, okay, at what time did this happen? I'm going to have to go perpendicular to the T prime axis to find out when that is. I don't go straight across, right? Or, sorry, I don't go straight across. No, wait, sorry, back that up. I'm going to have to find out where this happened, meaning that I have to look at, not perpendicular. I want to go parallel with the T prime axis to find out what position it was at. That's what I was trying to say. Because look, there's a difference in the spacing of these two axes. So I have to go backwards like that, right? In order to find out what's the x coordinate, that would be my x prime coordinate for this event happening. Oh, that doesn't look very parallel. Sorry. It's supposed to be parallel. I thought that distance looked a bit big. All right, so it's maybe more like this. Maybe it's more like that. Okay, so there's x prime. And therefore, this distance here would be the same as this distance here. That's just v times t. right? And I got a little ahead of myself with the time, but the time as seen from the car frame, and according to Galileo, that time would still be this time as marked on the t prime axis. It's because t prime equals t from the Galileo transformation perspective. Nonetheless, what I want to get across here is not that that's happening, but if I want to find the correct position of this event according to the car frame, I have to go parallel with the axis. Right, like this. I have to go parallel with the axis. I said perpendicular, that was wrong, sorry. I need to go parallel with the axis in order to find the prime coordinate here, okay? The x coordinate's over here, right? That's the x coordinate according to the tree frame. This is the prime coordinate according to the car frame. Okay, so that being said, we have one more issue to talk about. And what I'm going to do is now let's go to the tree frame, and let's say, well, let's do this. Let's go to the car frame, and let's take a look at what happens if I take the baseball and I turn it into a light beam instead. Okay, so instead of throwing a baseball, I throw a light beam. The question then is, what are we seeing? So if the ball becomes a light beam, we know that according to the tree frame, we know according to the tree frame that the car is moving with respect to us, okay? Now, if I'm on the car, and I shoot a light beam, if I turn on my flashlight or a laser beam or something and it goes, then according to me, I'm not moving, the tree's moving back that way, and the light beam's going this way, and it should be going at light speed from the car perspective. Okay, but what does that mean from the tree perspective? Because the car was moving with respect to the tree perspective, and therefore, if I look at the regular Galileo transformation, and you know this from common experience, is that if you throw a baseball or a tennis ball, it goes a certain distance. But if you're in a car and you throw a baseball, doesn't it go? If you're sitting on Earth and you're watching somebody throw a ball, it goes a lot faster if they're in a car and moving with respect to you, and then they throw the ball. However, if you're in the car and you throw the ball, it just goes like it does on Earth, right? So the question is, what happens to the light beam from the tree perspective if I'm in the car and I let a light beam go this way? Then according to me in the car, it should be traveling at light speed. But what happens from the tree's perspective? The tree perspective would say, well, you got to be, that light beam would then have to be traveling at car speed plus light speed. Because that's how the Galileo transformation works, right? If you look at the answer that Galileo gave us, Galileo says that x prime equals x minus vt. Okay, now if I just time differentiate this entire thing, then I'm going to get that to be leading to dx prime dt equaling dx dt minus v. In other words, what does the prime frame see as the speed of the event? This is say w prime equals w minus v. Now v, we already know, is the speed of the frame with respect to one another. It's right, oh, where is it? Right there. I see it up there, but I can't point to it. It's right there. V is the speed of the car with respect to the tree. Okay? So the question is, how fast am I throwing the ball? Well, the ball speed, as seen from the car frame, is what you see from the tree frame minus the relative speeds of the two. Okay. But the question is, what if this is C? Or what if this is C? Then if I change frames, do I observe a different speed of light? Okay. And so you'd ask yourself, well, okay, how on earth are we going to figure that out? Let's see here if I can show you this. Let me share my screen here, and show you what I have here. Let's see. Where do we go here? Share screen. Whoops. Okay, here we go. Okay, there we go. Here we go. This is what we expect. So here is a light bulb, and it's initially at rest in the say the tree frame, and we put it on a car, and now it's at rest in the car frame. So the question is, what does an earth observer, like a tree observer, see when light is emitted by the light bulb? So here's the light bulb at rest, so everyone says light speed is c, but here's the car moving with the light bulb in it, and now people say, well, this is c plus 100 meters per second because the car is moving 100 meters per second. C minus 100 meters per second. It's in the airplane now, okay? C plus 1,000. Here it's in the rocket ship, C plus 10,000, okay? Makes total sense, right? After all, we know that if we are in a car and we're throwing a baseball or we're launching an arrow or doing something, right? That, in fact, and Mythbusters has a good video of this where they try to match the speed of a truck to the speed of an air cannon, and they launch it out the back. And boy, I could see if I could find that video. But what they do is they try to measure the speed of this ball shooter, and then they match the truck speed, and they mount it to a truck bed, and then they try to match the truck speed to the ejection velocity of the ball, so that as viewed from the ground, the ball just falls straight down. Because the truck's moving this way, the ball gets shot that way, and from our perspective, those speeds are exactly the same. So from the Earth camera, the ball just drops, okay? Because they matched velocities. So the question is, can we do the same thing to light? Can we have a source moving so fast that way that when it ejects light this way, light's just standing there? Because, right, it seems like the observer on the left here, C minus 1,000, C minus 10,000, all I got to do is make it C minus C and the light will be standing still, right? That'll work. Won't it? I think it will. I bet it will. It's not going to, though. This is what happens. This is what happens. Experimentally, people have measured the speed of light as it is ejected from moving sources, and those sources have been moving very, very fast. Sometimes the sources are even moving at 99% light speed. So the source moving at 99% light speed ejects light, and we still measure light to be light speed. Light moves at light speed. And that's really all there is to it. Light moves at light speed, no matter what. No matter who's observing it. And this is such a fundamentally strange thing. It seems like a really easy thing to understand. Maybe you've heard this before. Light travels at light speed. And it doesn't matter how fast you're going. Light's still moving at light speed. But think about that for a minute. No matter what speed you're going, light is always going the same speed. And that is kind of strange because we basically never experience that. We don't have any direct experience with this, okay? And this leads to consequences that therefore seem strange because we have no experience with that. So, if light travels at light speed, we have a slight problem with the space-time diagrams then. That's incidentally what these are called. Space-time diagrams. We have a problem with the space-time diagram, okay? Because, let me draw it for you. I'm going to use this one. I'm just going to redraw this. a little bit more this way so I've got a bit of room. All right, so I'm going to go to the tree frame again. Here's the T, and I'm going to give myself a little bit more room this way. So here's my x-axis. Okay. So let's take a look at what this means from the car perspective. So here's my car axis like this, T prime. Okay. And then the car ejects light. Okay. So light is moving back and forth. Suppose we do this. We eject light in both directions from the car. Okay. Both directions. So light, excuse me. Whoops. Well, that's not what we wanted. Well, I drew it this way, so let me change my question a little bit. Let's suppose this. Let's suppose that I'm in the tree frame and I have a light bulb that I turn on and someone's moving past in a car. Let's start with this one because I ended up just drawing that one by accident. Okay. We're going to stand here in the earth frame and we're going to eject light in both directions. So there it goes. Okay. Now, the car is moving past at the instant I eject light both directions. Okay. In other words, everybody corresponds down here at 0. I eject the light at 0 and the car moves past at exactly the same time. So what happens? If light travels at light speed, which by the way is an experimental fact, okay? That means that I'm going to measure the distance from the tree to the light beam. At the same time, I'm going to measure the distance from the tree to that light beam. And so what I'm going to say is, look, here I am, I'm at the tree. I'm going to measure this distance here because to measure distances, all I have to do is go parallel with the space axis here, right? This gives me at the same time, a measurement of the distance between the tree and the light beam on this side and the tree and the light beam on this side. I was in the tree frame when I ejected these two light beams like that, and therefore they travel the same amount of time, and therefore they should be the same distance apart. And I think you can kind of see that these two distances are exactly the same. Great. Problem. The car. The car's moving, but the car is supposed to also measure the speed of light being c. And therefore, if I look at the car from the car's perspective, I'm going to say, well, wait a minute, look. If I use that kind of reasoning, there's the distance to the light beam that I'm trying to catch up to, but here's the distance to the light beam that I'm leaving behind. And I think you can see those two distances are definitely not equal. Yeah? So the space-time diagrams have to be modified. Okay? They have to be modified. Now remember, when you want to measure something, you have to go parallel with the axis that you're trying to measure. So this must not be a valid way to measure space distances from the car frame. This is not the way to do it. The way to do it would be these two distances have to be equal. Okay? These two distances have to be equal. It's an experimental fact that light travels at light speed no matter what your motion is. And incidentally, this is why Einstein did not like the name of relativity theory. Because everybody, you've heard this a million times. Oh, it's all relative. No, it isn't. Light travel is not relative. Everybody measures light travel to be light speed. And so Einstein wanted the name invariance. Light speed is what's called an invariant. Okay? Talk about that in a minute, but I want to finish my thought here. How do we make the measurement of the distance from the car to the front light beam and the car to the behind light beam to be the same distance? Because they have to be. Now, note, they don't have to be the same distance as the tree measured. The tree may be measured 5 kilometers that way and 5 kilometers that way. The car doesn't have to measure 5 kilometers, but it's got to measure something and the same thing. Either, right, both directions. Both of them have to be the same. So how do we do that? Well, if you go like this, well, I can't quite do it, so I'm gonna have to move this down a little bit. If you go like this, I'm going to take a measurement here of the distance. Let's say it looks about like, I'm going to say like that. The distance from there to there, and the distance from there to there. No, not quite the same. Let's tilt it a little bit more. If I take the measurement of the distance from, say, here to here, oh, that's going to be too high. I'm going to go the measurement from here to here, from here to here, and then from here to here. Not quite enough. Maybe I need to go down. Maybe that's what I need to do. I'll go this way, and this way. Oh, that's what I need to do right there. Look at that. Those are pretty close. Okay. So this does not work, but this does, because those two are the same size. I have to tilt my space frame, my space axis, just like I tilted the t-axis here. Okay, so what that means is we have to draw the x prime axis being there. Notice that these measurements are parallel with that axis, or at least they're supposed to be kind of close to it. They're supposed to be parallel. Okay. When you are in a moving frame relative to another one, I already told you can look at both perspectives from the same set of graphs, but you have to make these modifications. Number one, the time axis has to tilt. Number two, the space axis has to tilt by the same angle up from the x-axis. Okay, so if you measured a certain angle here, say theta, then you had to measure that same angle here, theta. Okay, and that, by the way, that theta depends on how fast you're moving. All right. Now you can look at what happens from both perspectives, and it will be what's called relativistically correct, because light travels at light speed, and therefore the distance from the car to the light beam has to be the same on both sides. Therefore, if I make a simultaneous measurement of the distance that way and the distance that way, simultaneous means it's at the same time. That means I've got to be parallel with the x prime axis. Okay, so I've got to make a measurement that's parallel with the x prime axis. And I guess I missed the parallelism a little bit there, but I'm telling you, those things have to be parallel. Okay. Okay. I got two things to say, and then we're going to do an example, and we're going to try to make some interpretation of these things. All right, we'll get started on our own figuring out of this. Okay, number one. I was going to talk about invariance theory. Okay, so back to that idea that I just mentioned about Einstein wanted the name of the theory to be invariance theory because light speed is an invariant. Notice that we have different words in physics for things. Now, if you've had, you're in 4C now, so you've at least had 4A and possibly B. We have several ways of describing things. We have things that are a constant. Okay, so for example, you have, what's a constant? So a constant is something like, say, the charge of an electron, right? Or the permittivity of free space. Or what's a constant? The gravitational strength, capital G. Okay, these are constants, right? They're in there in order to massage the numbers and make our unit systems work out and things like that. But nonetheless, they're constants. Possibly you used to think of the speed of light as a constant, and we're about to move speed of light into a separate category now. Okay, so we have things that are constants. We have things that are conserved. We have quantities that are conserved. Energy is conserved. Linear momentum, angular momentum, right? These things are conserved quantities, which means that for this observer, they were the same before and after an event happens, okay? The problem is you have to be the same observer. I can't say that the person in the tree measured the same energy as the person in the car. So I can't say that oh, the kinetic energy of maybe say the baseball, back to the baseball question, right? The baseball is moving at a certain speed. So the tree frame person calculates a kinetic energy, and then the car frame person calculates a totally different kinetic energy. So you can't use conservation of energy between frames. It won't work. But in one frame, you can say, yes, it's conserved because I'm going to calculate the kinetic energy and I'm going to calculate it here and here, and it's going to be the same. Okay? I'm avoiding gravitational potential energy because technically in special relativity, there is no gravitational potential energy because we're a constant motion in a straight line. Nonetheless, conservation of energy works if you are in a frame. It does not work if you start in one frame and end in a different frame. You can't compare those, okay? Same thing with constants, typically. You don't, well, sometimes they work the same way, sometimes they don't. Point being here that when we get to the next category of things called the invariant. An invariant is something which is the same for all observers. Now, here's where speed of light now resides. Okay, it's not a constant. It's not a mere constant anymore. It's an invariant. So everybody measures speed of light to be light speed. Okay. Now, there are other invariants, and we will talk about some of the other invariants probably tomorrow. Not quite yet there today. Nonetheless, speed of light is an invariant. And that is such an important thing. I'm going to write that down. Speed of light is invariant. And what invariant means, same to all observers, okay? No matter how they're moving. And here in special relativity, you might ask why special? We've heard of the thing called general relativity. What's the difference? Well, special relativity is special because it comprises only constant speed motion in a straight line. In other words, it's inertial motion, okay? That's a pretty special kind of motion. Basically, almost nobody has this, except maybe you're on a train. Even then, you can feel the bumps and you can feel the motion of the train, usually. If, for example, it's really smooth and you look out the window, you don't realize you're moving. And then you look out the window and you see, right, things going past. You don't think, wow, look at Earth moving past that quickly. You think how fast we're going through the landscape. But really what you are able to think is, wow, Earth really is moving fast the other way, right? Of course, but I'm saying start taking that away, right? This is how you start seeing perspectives of others, is by forgetting who's moving technically. You always think you are not moving. And everything moves relative to you. So it can be very egocentric in that sense. It's the same to all observers. So what does general relativity mean? General relativity is a theory of accelerated motion. Okay, it's therefore consequently also useful for gravitation, which is where you probably have heard of it most often. But it's really an accelerated motion theory. And that means it supplants Newtonian mechanics. Okay, it's actually the thing that now you can use instead of Newton's F equals ma. You can use the Einstein field equations. Turns out it's a little more difficult, but they give you technically a more correct answer. Because Einstein's GR agrees with nature better. It agrees with experimental results better than Newton's does. So anyways, nonetheless, Newton's works really well for us. We're big, we're slow. Newtonian mechanics is great. Okay, so that's special relativity. That's an invariant. Let's talk about looking at a space-time diagram and making some interpretations of it. Oh, wait, I got one more thing before we do that. Because we can't look at the space-time diagram. I did it on this one, and you probably noticed, you go, wow, speed of light's not very fast, is it? Remember that 1 over v is the slope here. 1 over the speed of the thing is the slope. So if I have a really steep slope, typically in 4a, you would have said, oh, because the axes are reversed, you would have times distance, right? This is actually a really slow speed. The really fast speed should be down here. So why is speed of light way up here? Why isn't speed of light way down here? Because ultimately, you probably know what speed of light is. Speed of light in SI units, we're going to say it's about equal to this. 3 million meters per second. Try that again. 300 million meters per second. It's a little bit less than this, but nonetheless, we'll just round it to that. So why did I draw it way up here? Well, what's that got room for down here? All these other things that are moving way faster than light, right? No, it's a scaling issue, okay? If I did this diagram in meters and seconds, where would light speed be? You wouldn't see it deviating from the x-axis hardly at all, because it's going at such a huge distance in such a tiny bit of time that basically light speed is flat and it's on top of the x-axis for us. For normal distances and times, I'm not going to see it. I can't possibly see it. It's way too fast. So we're going to change our unit system. Okay, we're not going to use 3 times 10 to the 8th meters per second unless we really have to. Okay, we're going to change our unit system. And the question is, why do this? Well, one reason is so that we can see it on a space-time diagram. Okay, what are we going to do? So here's the question I have for you. And just as we thought speed of light was just a constant number, it's not. Now we know it's something even more shining and glorious than that. It's an invariant. Okay, what is it telling us? In the SI system, what is this thing? It's a conversion factor, right? It's a conversion factor. It converts meters or it converts seconds into meters, say, right? Converts seconds into meters. Why do we have different measurements? Why do we have different units for time and distance? Why do we do that? Convenience for humans, certainly, right? But from a physics standpoint, what's the point of having a second for a time unit and a meter for a space unit, and then having to convert between them using this number? Why don't we simplify our lives from a physics standpoint and make this number way simpler? 3 times 10 to the 8th is a huge number. I can't comprehend that number. I can comprehend a better number, like 1. That's a number I can comprehend. So why don't we just say that we're going to start measuring time in meters? Why have different units? Why? There's no real physical reason for this. It's just human convenience, okay? If I start measuring, right? If I start measuring time in meters, how the hell are we going to do that? Well, we're going to use this. We're going to use this thinking right here. Now, remember, light speed is an invariant, okay? So what I can compare speeds of things to light. So I can say, if I want to consider a distance, if I want to consider a time, I can measure it with meter units. How do I do that? I say, in this time, how far would light have traveled? That gives me a genuine thing that I can compare other times to. Okay? So ultimately, I'm going to change the units here. And we can get into a whole bunch of talking about why and how and this and that and the other. But ultimately, seconds and time and distances should be on equal footings. We should be measuring them in the exact same units. So we're going to change light speed to 1. Change light speed to 1. 1 what? 1 meter per second? No, I can't do that. That's not the speed in those units. But I can change it to 1 meter per meter. Okay? 1 meter per meter. That's what we're going to do. Therefore, when I compare someone else's speed to that, suppose you're moving at 0.8, okay? You're moving 0.8 meters per meter. Okay, let's talk about what these meters mean. The top meter, right, the one in the numerator, how many meters that you moved. The bottom meter is how many meters light moved. Okay. So I'm comparing how far did I go to how far light went. And that's a reason, I feel like that's a pretty easy ratio to figure out, right? We know, and you can even think of it in this way. But if you think of light as 1, and in fact it's even better because now it's technically unitless, because meter over meter, that's a nothing, right? Now c is equal to 1, and that's why it makes sense on the space-time diagram that I drew it at the 45-degree angle, because it's 1 meter of this to 1 meter of that. And that's why it's the 45-degree line, okay? That means all of the motion of all of our objects is going to be up here because, as you might know, nothing material will travel faster than c, and we'll get into a little bit more of that later. Can you move faster than light speed? Yeah, things can move faster than light speed. But for right now, we'll say, nah, it's going to be mostly up in here. Okay, so this gives rise to the ability of people to sense the connections between things, kind of causality effects, right? So something that is in where's it? No, something in Nebraska right now can't affect me. It can't have a causal effect on me now because light had to take time to travel from there to here, and it did so in I don't know, like a really little amount of time. Nonetheless, there is a cause and effect relationship between events. And you can say that events that happen out here can't have causal effects on events in here unless light can get there in that amount of time, right? So if I say, look, I've got an event happening here outside the light cone, right? It's way over there. And I'm interested in what's happening right here, I would say there's no way light could have traveled from there to there because it's less than a 45-degree angle, right? That's like having one of these out here. Light can't travel that fast, right? So there's no causal effect between these. So it gives us also the ability to determine cause and effect on the space-time diagrams, which is cool. All right, enough blabber. Get to what we're getting to, which is, let's take a look at an example here. So I'm going to share my screen. Am I? Gosh, I hope I am. Where's the thing I want, though? Got to find it. Hold on. Where is it? Just a sec. Just a sec while I go find where it is so that I have put the thing that I want. Okay, I want that. And I want, well, that's interesting. What have I done with it? Oh dear. Nope. Alrighty, and here we are. Wait, let me open this up. There so you can see it better. Oh, I see what's happening. Okay, this is what we want right there. Okay, all right, so let me share my screen so that you can take a look at this. And it is this. Okay, hopefully you can see that. I think I gotta make it a little bit less big though. I'm having trouble seeing it down there. Yeah, I gotta make it a little less big. Let's kind of push it. Okay, up, there we go. Okay, let's take a look at this space-time diagram here. I'll post this on Canvas so that you can have a better look at it and not a rather rapid and oh my gosh, what is going on? Look at it. let me set this up. So we have a car moving on the bottom of the picture there, and we have a person who is stationary in the earth frame at the bottom of the picture, and there is numbered 1, 2, 3, 4, 5. These are, say, lamps, street lights, say, okay? And they are turning on. They turn on at different times. Where do they turn on? Okay, so take a look. There's a lot of stuff going on in here, but this is part of what we need to deal with. Okay, look at the axes here. This axis is labeled CT. Nevertheless, just eliminate the C. It'll just be T. And then you'll see this axis down here is labeled X. You'll see the world line of the car here at T prime. This is the space axis of the car here. That's labeled X prime. Okay, so we have our two axes set up. We have what are called the world lines. That is to say, the motions of the street lamps. Okay. The motions of the street lamps in the earth frame is completely stationary. They do not move. That's why all of these red lines are going directly straight up. Okay? That tells us where they are in the earth frame as time goes on. Okay? They also tell us where they are in the car frame as time goes on, because you'll notice that eventually the car frame, according to the car frame, the street lamp number 2 passes it. Okay. So let's take a look. When do the lights turn on according to someone who is standing on the earth, in the earth frame? All right. Now, I'm going to give you two answers to this question, and I'm going to word them very specifically, and I want you to be aware of this wording. Okay. So I'm saying, in what order are the lamps turning on according to someone in the earth frame? Then I will ask the question, in what order does the person standing there see the light emitted from the street lamps? Those are different questions, okay? Those are different questions. Let's first start off by saying, let's figure out the order that the street lamps turned on. All we have to do is take a line which is parallel with our x-axis and go up. And that will be how time increases, okay? So here I'm going to look at it, and I'm going to take my x-axis, and I'm just going to imagine it going up, and I'm going to say, all right, the first one it reaches is C, is point C right here. Point C is when the street light number 3 turns on. Okay? Let's see. Is this also a point right here? I guess this is also a point right here. So simultaneous with point C is across from this dashed line here is point A, which I guess kind of didn't quite label very well there, but that looks like number 1 turns on right there. Okay, so A and C turn on simultaneously according to the Earth observer. I then go up to the next dashed line here, and I see that the next one up in the sequence is E. So E turns on, I guess you'd say second, because A and C were a tie for first. E is second. I go up, I see D, that's third, and then last I would see B turning on way up here. Okay? So that's the order in which the lamps have turned on. Now notice that this means that you are kind of all-knowing as an observer, okay? Because now the question I'm going to ask is, when did the light from the lamps reach the observer who's down there going like this, pointing at the lamps? In other words, when did that observer see the lights emitted from the lamps, right? In what order did that see those? So now I'm going to look at all the 45-degree lines that are emitted from those points. When do those cross the person's t-axis? So you'll notice that the first one to cross the t-axis here is the one from A, and it goes from there to there and crosses up to here, and that's when the person sees the light from A, from number 1 turning on. Okay? The next thing they see is the light from C turning on much later, right? All the way up there. So even though A and C turned on simultaneously, because 3 is further away than 1, you saw 1 light first, then 3's light. All right? Nonetheless, we know that they turned on simultaneously because of that delay. What do we see next? We see D turning on. That is next. It reaches there. And then, oh, and it turns on. And when it turns on and it emits its light, B turns on later. But look, you see those two lights simultaneously. You see them simultaneously. Last one you see is E. It turned on, what, second or third, and then it's so far away that its light took a much longer time to get to you because it's just a longer distance. All right? So that's the answer to first, what's the order they turned on? And that for that you have to be all-knowing, okay? You have to be able to see the entire thing. And then the second question is, when does the light, in what order does the light from the lamps reach the person's eyes? When do you see them? Okay? So those are two different things. We'll talk more about that. Now I'm going to ask the question, since we're just about out of time here, I'm going to ask the question, in what order does a person in the car see the lights turning on? Now I got to go back to A, B, C, D, and E because those are the events. Everyone agrees the light turned on, but in what order? Now I'm looking at the X prime axis and I'm taking a line parallel to the X prime axis and I'm going up with it. So from that tilted perspective, what happens first? Well, on the axis is C and E. So for a person in the car frame, C and E both turn on simultaneously. And then A and D turn on simultaneously a little bit later. And the last one is B. B turns on the last. So notice the dashed lines that are parallel with the X prime axis. That's how you tell simultaneity from the moving frame. Okay? You always go parallel with the space frame to find simultaneity. I'm going to repeat that many times. You always go parallel with the space axis to find simultaneity. And you already know this because every time you want what happened at this time, you go out, right? But now you're going, I want this happening at this time. Now you've got to go tilted, okay? All right, so that's the set of events from the car perspective. But I see that we are just about out of time here, so I will call that good for today. We'll pick this up tomorrow, where we will interpret a little bit more of space-time diagrams and get a look at some more consequences of special relativity. So that being said, I will say happy rest of your day, folks. And we will pick up again tomorrow. See you then.